Okay, we can restart now. So we came up previously with this formula, the generic formula that gives us the depletion layer width as a function of the voltage applied externally, and it was this one here, VBI minus V minus 2, all in this parenthesis. So, and remember that the picture we have in our mind is that effectively, if this is my P side and my N side, there is a depletion layer that is keeping separated the free carriers here and there. What does this remind us? Of all the passive electronic components we've seen up until now. Does this remind you anything? Capacitor, 2 plates. So this is what we should call as the depletion capacitance now. Depletion capacitance. Oh, the formula we will see is per unit area actually, just because we are not explicitly saying, you know, this is a piece of solid. We're not saying what is the area of this piece of solid. So the capacitance we will say is per unit area. Per unit area. Remember that the capacitance C generally is defined as the dielectric constant of the material time the area of the plates divided by the distance of the plates. So what we are doing now is calculating C over A, which generally is epsilon over D. So the only thing is that in our case, instead of D, we have to use W. So the depletion capacitance, which is generally indicated by CT, and remember this is, the units are farads per square meter in this case, just because of what I just said, we are going to do it per unit area, is epsilon over W. Epsilon, actually, what is epsilon? The dielectric constant of the material. In our case, this is the semiconductor, so epsilon S. So really, that's what the depletion capacitance is. And the nice thing about that is that it's a function of V, because W is a function of V. V is the voltage applied across the p junction. And based on what we've said previously, that if V is negative, we said W is large. So I'm expecting CT to be small. When instead D is moving toward VBI, W becomes smaller and smaller. And so CT should increase. So the theoretical, let's say, expectation is that if this was VBI, CT, the depletion capacitance, should have kind of this behavior. This is CT. I'm not sure why it's indicated always with this T, but that's how we will indicate it. In the books, you'll find it as CT. Okay. As I said previously, this is not exploding really. It's becoming bigger and bigger, but at a certain point, will kind of stop growing. This is this artifact caused by the assumptions we've made. Okay, so keep in mind, this kind of will stop growing at a certain point. It will become bigger and bigger, but it won't become infinite. That's my point. Okay, so that's really the depletion capacitance, and now we move to the biggest part, let's say, of this lecture, which is the current voltage characteristic of my PN junction. So before I start going through to understand, you know, why the PN junction has the electronic behavior it has, we will be making in everything we say, we are basing everything on 4 fundamental assumptions. remember, once you apply voltage on a device, you have equilibrium condition. We've dealt with non-equilibrium carrier densities in the semiconductor section. And you remember we've talked about a reasonable assumption that simplifies lots of things, which is the low-level injection. That is the amount of carriers that we are inducing, let's say, in a certain of the semiconductor, putting the semiconductor in non-equilibrium, still than the actual amount of majority carriers. You remember that part. So we can quantify that by saying that delta n, which is equal to delta p, this is the amount of carriers that are causing the non-equilibrium situation are smaller than the majority carriers, either in this side or that side. So let's put nn 0 or p0. These are the majority carriers on the n side. Majority carrier. So this is the low-level injection condition that we will assume. The other thing is we will keep assuming the abrupt depletion approximation just because it makes things so simple. And the other thing is that we will assume that within the depletion zone, there is no generation of carriers. Okay, this is free of carriers. If there are carriers, they are coming from this side or that side, but nothing is being generated in here. And finally, the semiconductors we're dealing with are non-degenerate. You degenerate. They are non-degenerate. You remember what it means? It means that the density is of electrons and holes is not extremely high. That's what it means. In terms of energy diagram, it meant that the Fermi level is far, at least 3 kT from either the conduction band or the valence band. Okay, go back, have a look. Non-degenerate semiconductors. So under these 4 assumptions, what we have in our mind is that, I will modify a little bit this diagram. Actually, I don't need to make it 3D. So what we have in mind is that, so within the depletion region, I have 0 carrier densities, zero free carriers. Here, I have these majority carriers at thermodynamic equilibrium now, and these are the minority carriers. And the minority carriers here are P and 0, and this is N and 0, the majority carriers on this side. So in my head, I'm thinking this situation. So no free carriers here at all. Here, this is the situation. This is the P side, and this is the N side. Okay, this is really actually a kind of a bit unrealistic in the sense that we've seen previously, we've built the energy diagram of the PN junction. And if you remember, it looked like this. It was at thermodynamic equilibrium, the Fermi level, then we had the N side here, and the P side here, and it was like that. So if this is the depletion region, so that's how the N side, P side. This is how the energy diagram looked like, if you remember. So what I'm about to say is that, yes, okay, fine, this is in our head, but in reality, to make sure that there is a thermodynamic equilibrium, in here, there is some free charges. And I can understand that actually from the energy diagram.
Hello everybody, sorry about this technical issue. It is clear that during today's lecture the camera crashed, and the camera that was recording the whiteboard. So what I'll try to do is but fortunately the microphone was still working, so we do have the audio recording. So what I'll try to do is to record separately a video based on my notes that will kind of try to follow what I say with my voice during the lecture, and I will then merge. I will use this part to kind of resolve the issue. It's only 15 minutes of video that is problematic, so I will try to solve it that way. Okay. So stay with me, and after this you will be able to continue to see the video.
Because we know, we've said it many times now, the distance of the Fermi level from the, for example, the valence band is telling me how much P is the piece of material. So you see, here clearly this is our P-type of semiconductor. But as I move along within the depletion layer now, the distance is increasing. So the semiconductor, if I read it this way, what is happening is that the semiconductor is slowly changing from P into N, slowly. So really, if I wanted to plot the carrier densities, I will plot here both the P and N carrier density together. We'll try to use different colors. So imagine this is Ni, the intrinsic level. So on this side, this is the P side. I have this is P, P0. There's a lot of holes and very little. I will use the other color. I will do first the holes. Leave it. So this is the depletion. How many holes are in the N side? Very little. Much below, this is Ni, the intrinsic level. Much below here. So by reading the distance between the Fermi level and the valence band, I understand that the holes concentration here is high, 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 starting to decrease a lot now, quite a lot. Here is very little. I'm reading the energy diagram. That's how the whole concentration changes throughout the device. And this down here is E and 0. So the whole concentration in the N side, the thermodynamic equilibrium. At the same time, I can do the same thing for the electrons now. So I will start on the other side. So here I have a lot of electrons. So how many? A little bit less than this density, because we said it's P plus N. So the density of electrons is less than this. I will do it just a bit lower. In my mind, I'm assuming this is a logarithmic scale, otherwise. And on this side, this will be the level of electrons. Here there are many holes, so very, very, very little electrons. Because this is a little smaller than that, this is a bit higher than this one. I remember the mass action law. So I'm reading now the difference between EC and EF. This has a lot of electrons, starts to decrease. The electrons decrease, very few electrons here. So this goes like that. And this is N0, and this is NP0. So all this noise, just to show you that, yes, fine, this is in our head, but in reality, thermodynamic equilibrium imposes this picture. This may actually be recombining, but that's actually the shape. We are not dealing with the fate of these carriers. We know that thermodynamic equilibrium, though, imposes this shape. Okay, maybe they recombine. We don't care. That's all. Okay, so this is the situation in terms of charge densities, both for electrons and holes, at thermodynamic equilibrium. We will come back to this. I've divided the understanding of the current voltage characteristic of a depletion junction in two parts. One qualitative, which goes through energy diagrams, and one quantitative. For the quantitative one, we will come back to this. We'll do it later. So now I want to deal with the qualitative one. So how do we understand the... Yeah. There must be some sort of equilibrium, and that's where I didn't want to say that, but yeah, it's there. Okay. So just still for a moment on this. So at thermodynamic equilibrium, what we know is that So thermodynamic equilibrium for us means Nn0 times Pn0 equal Ni squared, or this is for the N semiconductor, or equivalently Np0 times P0 also equal Ni squared. So this is really for both sides a thermodynamic equilibrium. When we move to non-equilibrium condition, what happens is that Nn times Pn is now different from Ni squared, and the same Np times Pp is different from Ni squared. And remember, this is the non-equilibrium situation. What we did when we talked about non-equilibrium carrier density, and that's what we will briefly mention later on the quantitative part, is that when I have non-equilibrium, I immediately think to quasi-Fermi levels that we indicate with Fn and Fp in our notes. Okay? So think when we hear non-equilibrium, we immediately think quasi-Fermi levels for the quantitative part. But now I wanted to first do a very important qualitative part. Did I say quantitative? So quantitative later, and now qualitative, which should... I just made a few nice diagrams on my notes that you will have. So there is no need really not to write down, because these are notes you will get later today. And let's just focus on what's going to happen. So this is the picture of my energy diagram. My energy diagram at V equals 0. I'm assuming this side, the end side, always at 0 volts. This is our reference potential. Okay? We are at equilibrium, so no voltage applied. And so the Fermi level is flat. And this is the energy diagram we've now come to know very well. Okay, so on the P side, what charges do I have? Well, it's P side, so a lot of holes that are distributed in energy, you remember, and very little minority carriers, which are electrons. At the same time, on the N side, I have lots of electrons and a little bit of holes. So there is no external field, but we now know there is an internal field. So really, we can call the total electric field is directed like that. So under this total electric field, what are these charges going to do? So the electric field is pointing like that, which means electrons should move this way. So all the electrons that drift move this direction. So this electron could drift in this direction. Holes that drift move in that direction, according to the field. So this hole will move in that direction. It is drifting. Okay? Now, there is something else, though. We are at equilibrium, remember. The Fermi level is flat. Are you expecting to see any current? Nothing can happen. It's at equilibrium. No current will flow. So we already understand that there is something, in equilibrium, there are different things happening that the overall cancel each other. So we said the electron is drifting and this hole is drifting. On this side, where I have a lot of charges, some charges, so these charges are too low in energy. They see a barrier in front of them. These carriers could move in that direction because of diffusion, but there is a barrier in front of them. They can't move. These two. But these could move in that direction because of they have a high energy, higher than the barrier they see in front of them. So really, we now get to the point I was making before about the equilibrium between different things. In equilibrium, charges are moving. Simply, they cancel out. There is some drift and some diffusion. They're all current zero. Okay? Same happens for the holes. Huh? So there is, which are the total drift current? Where the electron going like that correspond to current going like that. Holes going like that, current going like that. So total drift going like that. Total diffusion, well, electrons diffusing like that means current like that. Diffusion current. These are diffusing this way, so they sum. Diffusion total this way. I've made them the same length just to amplify the fact that these cancel out. So total current zero. Okay, so with this nice picture now, we will see how the PN junction operates. So we can see that is a mixture. We are anticipating it already. Mixture of drift and diffusion. Drift could be from minority carriers or majority carriers. In this case, is the drift of minority carriers. Drift of minority carriers and diffusion are balanced. Okay. Second situation. So this was equilibrium. Let's see now reverse bias. So what we are thinking is reference potential here, negative bias applied here. So this means, according to what we said previously, we take this side of the band diagram, we move it up by QV. And I've drawn, you see, Fermi level. This is the Fermi level. You see, this is the line representing the Fermi level brought from that side. So this shift is QV and goes up because V is negative. Negative, negative, positive shift. So I've drawn the three valence band, conduction, Fermi level, conduction band, and then joined the conduction and valence band together. So again, where is the total electric field going? The derivative here is negative. So the total of the conduction band, we know that this derivative links to the total electric field, and the total electric field is going like that. So again, these electrons could drift in this direction. These also could drift in that direction. Total drift current going like that, drift like that. At the same time, this could in principle diffuse. Oh, note, I didn't stress it previously. Diffusion is the other very important mechanism that we've seen. We did it in the semiconductors, we did also drift. The nice thing about diffusion is that carriers can diffuse in any direction. Here, they are going even against the field, the external field applied. So that diffusion is a very important process. Actually, for the PN junction is fundamental. So in reverse bias, these cannot diffuse in that direction because there is the barrier they can't overcome. Okay, so really in reverse bias, everything is ruled by the drift of these minority carriers. The drift, the minority carriers are very few. That's why I'm expecting that this current is extremely small in reverse bias. I can already anticipate that. Okay. Let's move to small forward bias. Remember, we've identified VBI. Okay. test. Yeah. So remember, VBI is a key characteristic, let's say, bias for us. So let us assume that V is smaller than VBI. It's positive, but smaller than VBI. So this is the kind of situation we are up against. So the Fermi level on this side is, V is positive, so there is a shift downward, but of small amount, as you can see. So overall, the picture is this one. Still, there is an electric field that goes like that. So the picture is very similar to the equilibrium one. The only thing is that now this barrier is much smaller. So the only thing is going to change is that now these charges will diffuse in this direction, but are more than previously. So in this situation, diffusion is starting to dominate over the drift of minority carriers. There is no more balance now. Now diffusion is dominating. And so overall, the current is starting to move in this direction. Okay? Now we are in reverse bias. The current was going like that, but was small. Now the current is like in this direction, and is starting to become bigger. These are really a lot of carriers here. Eh? Okay? So we start to understand that in forward bias, the current will be very big. And finally, in a high forward bias situation, which means, you know, now this whole side is going down, this is positive, so this has to move downward. Now, you see, now the total electric field has switched. Now is like that, the derivative is positive, the total field is like that. This means that these carriers can drift now, are moving again, opposite to the direction of the electric field. So these are actually now drifting. These are also drifting. So now everything is just drift. The PN junction has effectively become like a resistor. We saw that when we did the theory of mobility and drift, that the semiconductor in the end could be looked at as a piece of resistance, a certain resistance, and all related comes down to drift. So really, when the voltage becomes very, very high, the semiconductor, the PN junction becomes a resistor in the end. And here the current is huge because these are really a lot of carriers here, and the same here. And they are all moving, contributing. And so in words, we have now described what is really happening. And this is the qualitative approach. I do like the qualitative approach for a physicist because it gives you the possibility to visualize immediately things. The quantitative approach is an absolute mess and disaster, and we will not do it because it's quite complex, but we will do some bits and pieces just to give you an idea of how it works. And so as I anticipated, in the quantitative approach to calculate the final current, what you have to do is to think to, because we are in an over-equilibrium condition, to consider quasi-Fermi levels. And remember that quasi-Fermi levels are related to the actual density of charge carriers through these equations. We've done this some time ago. Now, but what I wanted to show you here is actually these diagrams that explain in a way the kind of assumptions we are doing here to be able to do the calculations. So when we think of, this is the diagram we saw previously when we are at thermodynamic equilibrium. Fermi level, the same everywhere. And this was the picture of the carrier densities within the junction. Now, when we consider forward bias, so you can see here there is a small forward bias. The Fermi level here has come down a little bit. Because we are in this non-equilibrium condition, and we want to introduce quasi-Fermi levels, how do we introduce them? It all comes down to drawing these lines that have been drawn here. So on the P side, holes are the majority carriers. So the assumptions we do in order to do the analysis is the quasi-Fermi level for hole, which coincides on this side, quasi-Fermi level for electron and holes in this side coincide together. When we are approaching the depletion zone, we'll actually stay there up until the end of the depletion zone. This is for what we call FP in our nodes. Here is indicated as EFP, doesn't matter. Okay, and then we'll slowly, gradually move toward the Fermi level on the other side. This is for the quasi-Fermi level for holes. So stays flat up until the end of the edge of the depletion layer. Similarly for the electrons. So on this side, the electrons are the majority carriers. So we assume that the quasi-Fermi level stays flat up until the end of the depletion zone. And then slowly and gradually goes back to the value of the Fermi level down there. So these are the quasi-Fermi levels. Remember, the quasi-Fermi levels can be read in the same way we use the Fermi level. So previously we used the Fermi level, or maybe the relative position of the Fermi level with the other energies to construct this diagram. We do the same here, just using the quasi-Fermi levels. The only difference is that when you use the quasi-Fermi level for electron, you are only at the conduction band, because the quasi-Fermi level for electrons is only for electrons. So, for example, let's try to reconstruct this. Let's look at the quasi-Fermi level for electrons. So I will try to reconstruct this curve. So here, the Fermi level is close to the conduction band. So I'm expecting a large number of electrons, large. At this point, it starts to, the distance starts to increase from the conduction band. So I'm expecting this very large number to start to drop a little bit. Here, then, it drops even more, even faster. So it stays high, then drops. In this region, it drops. And then during this region here, it keeps dropping until it goes to the low value that, in the p-type is, now the electrons are really few. So I'm expecting this type. Eventually, it will, the density of electrons will become the density at equilibrium, which is NP0, eventually. Similar story for the whole. So now I compare this to that. And what I notice is this out of equilibrium condition that, you see, here and here, there are more minority carriers than there should. You see that the actual density of minority carriers is more than Pn0, or in the same year. This clearly indicates that we are outside the equilibrium situation. In this situation, you have, if you do the same story, you will actually realize that you actually, this is the reverse situation. So the depletion layer is larger now, much larger. And so what you do here is actually that you are depleting, if you like. You are well below the equilibrium value. So even just by looking at this carrier density diagrams, we realize that this is what in the calculation we do. So if this side has more electrons than it should, it has to throw away these electrons to reestablish thermodynamic equilibrium. So there will be a current of electrons going like that. The same for the holes on this side. The holes need to go away from here to remove holes so that we tend to reestablish thermodynamic equilibrium. That's what the semiconductor will try to do. So a current of electron in this way means a current in this way. A current of holes in this way means a current in this way. So total current in this way. So in forward bias, the current is moving in this way, which is exactly what we've seen also previously. So this is a different route to see the same thing. And same story here. In the same story, similar story. Here we have less electrons than we should. So we need to add electrons from the external circuit. And similar here, there is less holes. We need to provide holes. And so total, the current is going this way. The current, though, here is small, because these are minority carriers. And the amount of charge required to refill this is very small, because these are minority carriers, are very few already. So in a way here, we also can recover the fact that the forward current generally is large, because this can be as large as the majority carrier levels, while this one is small, because the minority carriers are anyway small in number. So anyway, long story short, we start thinking to quasi-Fermi levels, and then we use the continuity equation. So I need to remove this. So we need to then use the continuity equation. From the continuity equation, we can, for n and p, which from the continuity equation, we can actually find p as a function of the position and n as a function of that. And this, as we've seen, this relate to f, p, and fn, to the quasi-Fermi levels. And then we can demonstrate, I have the demonstration here, so again, I won't do it here in class, but the demonstration is quite simple, that Jn and Jp, you remember we've realized that the current densities for electrons and holes are generally made of a part that is drift plus a term that is diffusion. Same here. Now we can demonstrate, using again some very simple arguments, that we can write these terms simply. We already know that if the derivative of the Fermi level with space is 0, there is no current. So what do you expect that I'm going to write here? Something related to the derivative of the Fermi level. So we can actually write that this is n, mi n, sorry, just a moment. Yeah, P, mi P. Okay, this is in general. Now, in this case, we were dealing with non-equilibrium. We should replace this derivative with the derivative of the corresponding quasi-Fermi level. And this one here with so we use this, and then we calculated the finally J as Jn plus Jp. I'm now describing you the process of what people would do in order to find the final result. And the final result is is that J J0 E where J0 is E so this is the diffusion coefficients that we know of, minority carrier densities, and this is called the diffusion length, and this is the square root of dp tau p. So tau p is the lifetime of the minority carriers, and this similarly the square root dn tau n. Now note that this term relates to the n side. This term relates to the p side. This is the density of electrons on the p side. Also, note that J0 is a function of temperature, because all these things are a function of temperature, and effectively depends on temperature in this way. E to the minus Eg over kT. So if temperature goes up, J goes up. If Eg goes down, J goes up. And this we can plot. This board is a nightmare. I don't know why it's like that. So this is J. This is the voltage. Remember, J is the current density. If we multiply J with the area, the cross section of the device, we get the current. So we will generally go from J to I. It doesn't really matter. And this looks like that. I'm exaggerating. Okay, this is minus J0. Sometimes J0 is also indicated as JS, they say. So in reverse bias, the current is minus J0, and that goes up exponentially. And so as we've described previously, in this region here, we have mainly the drift of minority carriers. Up to VDI, we have mainly diffusion, and then again, mainly drift. That's what we understood. And from this kind of plot, which I will do again here, just to point out some more things. We realized that the PN junction is actually a variable resistor. And to see that, I will plot IMV, just because we are used to see resistances with IMV. On this plane, a resistor is a straight line. The slope would be 1 over R. Now, the characteristic of the diode is this one here. So I equal I0 e to the EV over KT minus 1. So if I take a point here, I can see that I could imagine here this straight line, which is the line representing effectively the resistance of my diode, because if I do I over V, this represents the inverse of a resistor, isn't it? We know that V equal R time I. So this line represents a resistance. This is a resistance, which if you, by using this it's a special resistor, a very complex behavior. Yes, as you move this point along this line, you get a different resistance. If you take this point, the line will be different. Unfortunately, I don't have millions of colors, but I can do this. Another resistor. So we can see that as we move this point over the, oh, this is, be careful, these are all DC values. So this is really this resistance that we're talking about is a direct current resistance. It's important because the next thing, which I won't be able to do it here, I will put it in the post-lecture video. It was the last bit I wanted to do, is the differential resistance, and actually which also brings to the diffusion capacitance. So this one here that represents the DC resistance of my diode, which is when I apply a certain voltage, how much current flows through. This is divided by the ratio V over I. This identifies a resistance. And on this plot is this line. Okay, I'll stop here. So I will put on the post-lecture video this last bit that was the differential resistance now and the diffusion capacity. I don't know what happened with the video. It seems it stopped. So probably I'll probably dub it. I'll do it with my notes. And you will see myself again dubbing myself. Anyway, okay. Tomorrow morning we do the tutorial, which will obviously be much, much lighter than our lecture on chapter 1. So we will deal with the quizzes and anything else we can come up with. Okay.